Morning, Prof. Isham. How are you doing?
Good morning. Sorry.
Morning. Yeah, it's okay. So, you familiar with the controls? Is everything okay on your side? Like test your mic.
Let me just check.
Okay.
So I just share content, is it?
Yeah, you share content.
Is it visible or?
Yeah, it is visible. Yeah.
Let me just go to presentation mode.
Yeah. Let me see.
Is it on the presentation mode?
Yes, it is. Yeah, it is visible. So I think everything's okay for now.
Let me just check with the animation, the only animation that I have.
Okay. Spherical cow.
Okay. That's good. Okay. Right.
Okay, so everything is working well, right? So yeah. Thank you. Thank you for coming in early. And thank you for preparing the slides and everything.
No
Yeah.
problem. So I just keep this thing on, is it? Or do you?
I think you temporarily stop sharing first until around,
Okay.
yeah, until around the top starts. Yeah.
Another thing, it's okay for me to wear a t-shirt, right?
Yes, it's perfectly fine.
Are there any guests of honor?
Guest of honor, I think
I mean,
we don't have any. Yeah,
officials or something.
I think if I'm not mistaken, we don't. We never invited. Unfortunately, we didn't invite any guest of honor.
Okay. I mean, the reason is basically if there is, then I should be also addressing the person.
I see. I see.
As anyone.
As far as we,
From the
to our
channel.
knowledge, I think no, right? No. Yeah.
Okay. Great.
Test mic 1, 2, 3. Test, test, test. Can you guys hear my voice clear enough?
Yes.
Thank you. Hello and welcome everyone. There is a friendly reminder before we start our event. Please make sure your mic is on mute throughout the event. I repeat, please make sure your mic is on mute throughout the event. Ladies and gentlemen, may I have your attention? This program will begin shortly. Please take note that participants will have to stay throughout the very end of this program. Once again, I would like to remind all of you to mute your mic throughout the program. Attention to the audience joining us to Facebook. You will experience a few second lagging because we are streaming using OBS Studios. Truly sorry for the inconvenience. Good morning and Assalamualaikum everyone. Before we start our event, may we all rise and be one in my body and spirit as we rise and thank you to God for this beautiful morning. Al-Fatiha. Amin Amin Ya Rabbal Alamin. It gives me immense pleasure to welcome all of you to our first keynote speech, The Physicist, Some Words of Thought. I am Nabila Fitra Bintin Osman, who will be joining all of you as the MC for today's event. As today's program, there will be a Q&A session at the very end of this talk. Therefore, you can turn on your mic to ask question or you can type the question in the link Padlet will be given during the session. Again, please make sure your mic is on mute throughout the talk. Before we start, allow me to introduce the speaker for our today's talk. Our speaker is Associated Professor Dr. Hishamuddin bin Zainuddin. Professor Dr. Hishamuddin is a research expertise in quantum information and foundation of quantum physics, geometrical and topological method in physics, complex network and information geometry, and mathematical cosmology geometry of space and time. Graduated with flying colors at University of Adelaide, Bachelor Science with Honour in 1984, University of Cambridge, Certificate of Advanced Studies in Math in 1987, and University of Durham PhD in 1990. He has various of experience as council member Southeast Asian Theoretical Physics Association from 2014 until now. Fellow of Malaysian Institution of Physics 1998 until now. Former Deputy Director of Institution of Mathematical Research, University Putra Malaysia from 2012 to 2019. Well, I believe Professor Hishamuddin will be talking more about himself during his presentation. Again, let's give our speaker a digital round of applause. Alright guys, without further ado, let us lend our ear to our handsome and charismatic speaker, Professor Dr. Hishamuddin. Alright Professor, the screen is yours. You may start your presentation now.
Okay, can everyone hear me fine?
Yes.
Okay, great. So let me share this slides. Okay, Assalamualaikum and a good morning, everyone. So, I think first and foremost, I would like to thank the organizers who approached me to give this keynote talk. I was a bit surprised, but no, but I'm very much honored to actually give it, to give the talk, to share some of my experience as a mostly theoretical physicist. So let me start. So I give this particular title. There was a different title given to me, but I will try to explain later on why I rather choose this particular title. So I'm going to talk about the physicist as a expert who would have some kind of a way of thinking to solve problems. So let me go to the outline of this talk. So I will be giving some kind of introduction. Well, at least from my point of view on what physics is supposed to be. And then I will try to expound a little bit the way that physicists think in general. So there will be few categories. There could be more. So there are a few categories which are listed there on the outline. Can you actually see my cursor, by the way? Great. Okay. So the simplification, universality and generalization, things that we put into thoughts, which is actually beyond measure, and the way things are going, that we probably have to go beyond physics in the traditional sense. So this will be sort of expounded in the talk later on. And I will share you some of my personal journey as a theoretical physicist, and perhaps this would be more interesting than the other ones, but okay. So let me just move on. Okay. Oops. It's not seems to be moving. Let me just. Yeah, I think I have some problem over here. Let me stop sharing that first. Sorry about this. I think it just stalled. Share that again. And let's see if this works. The slides is not moving. Let me figure out what's happening.
Hi, Prof. Isham. Perhaps we can ask Shamini, or perhaps our host, to help you share the slides. Is that okay for you?
Okay, that would be, I suppose that would be better then.
Yeah, okay, we'll let the host to share.
Share that.
Yeah, sure, Doc. Prof, I'm doing that now.
All right. Okay, so let's move to the next slide, please. So as I said, the outline, there will be three parts sort of going through. So the first part will be the introduction. Next slide. Okay, and alternates. Okay, before I begin at all, there will be some disclaimer. As I said, I do not want this particular talk to be like a manual kind of thing. So this is not meant to be a manual per se. It's something like how to be a physicist. So it's nothing like that, and it's not intended to be sort of comprehensive or systematic. So these are just my own thoughts, and then essentially my personal recollection of experience, reading and understanding, and trying to do research. So being a theorist as well, with little, if not nil, experience in experimental physics. So I should something which is more common to both theorists and experimentalists. So I'll just focus more on the common flow of thoughts. So that's why the title of the talk is essentially some modes of thoughts. I wish I aspire to cover the whole of physics, but of course, that's probably most impossible for a single person to do. So there will be biases. So being a theorist, no, I will be more biased to the way that a theoretical physicist think, but you can actually extrapolate some of these ideas to experimental physics. Okay, for the next slide, please. Okay, it's, I guess the first thing to do is to define what physics is supposed to be. So how is it different from, say, chemistry or biology and other things? So I just look up a dictionary for that matter. So there's an online, Oxford online learning dictionary. So physics is claimed to be the scientific study of matter and energy and the relationships between them. So you can read the text there. So, but one should be also be very careful because normally the idea of matter energy is sort of presume or assume some kind of background space and time. So, but space and time is also the focus of physics. So that will be there as well into the definition of the study of matter and energy together with space and time. Of course, you can talk about in a much more general sense that energy may already be there in space and time. So again, one should also look at how physics are distributed across all types of sub-areas. So I think since 2016, the American Physical Society actually listed 18 disciplines. Okay? Initially was 17. And the American Physical Society did this in order to sort of replace the previously was the Physics and Astronomy Classification Scheme, PACS, which is handled by American Institute of Physics. So this is a bit more comprehensive and more flexible in some sense. And you can see most of the thing, it covers most of the areas of physics that you actually know. But there are, I think probably, I will mention this again later on. If you look at number 10 and number 17, that is essentially sort of a new addition to this physics discipline. Okay. So the next slide, please. Okay, it's good to have some kind of map of physics, and this is a cartoon physics given by Dominic Wallman. You can see the link down there, where actually organizes physics into sort of theoretical domains in some sense. You have the classical physics, relativity, and quantum physics down there, and he also listed philosophy. Normally what happens is that when you go to the frontier of research, you will look like to revise certain ideas, you probably need to know the philosophy behind those ideas and also how to construct new ones. So philosophy is also part of what physicists actually include as a mainly as a tool. Okay, it's not a kind of profession like the philosophers have, where they deal with very difficult questions, sometimes without answers. So physicists tend to be more practical in this particular case. And as I said, this map of physics are rather theory, what you call theory-laden kind of map. with the divisions between the classical physics and quantum physics. And relativity is actually in between because you can have both classical domain and quantum domain. But I just want to highlight the situation in Malaysia, okay, at least from my point of view. I'm not quite sure whether you can you point to the condensed matter down there within the context of quantum physics? Yeah. So I think for Malaysia, most of the physicists that I know, they tend to work on condensed matter. So you can imagine the map of physics in Malaysia, probably you get that area of condensed matter sort of blown up to say 80 to 90% of the whole diagram. And then you have all the little spots of the different other areas. So that's one difficulty probably I will mention later on in my personal journey. Okay. So, but essentially, coverage of physics will have all of these areas to include. Okay. So the next slide. Okay. Now I'm going to go into the idea of thoughts, okay, and the modes of thoughts that I wish to say something on. So let us think a little bit. This is actually an idea of Penrose, who won the Nobel Prize, I think, 2 years ago. So theories and models in physics, first of all, they lay claim that they are describing the physical world. Okay? So in other words, there will be this world, or the physical world that the physicist is trying to explain or describe. Okay? And then most of the time, whatever theories and models in physics will have to make use of mathematics. And mathematics are, in a way, used in physics as an efficient language. Okay? So you have this, according to Penrose, he will actually build a mathematical world itself. So he's a Platonist. So he says that there is this world of mathematics that sort of there, independent of the physical world. And finally, there is, of course, the way we construct how we do the theories and models, which are the mental constructs which come from our imagination, how we think about the world, and how we try to represent this in physics. So there are these interconnected worlds between the mental world, which our thought processes, trying to describe the physical world through mathematical world. Okay? So this is sort of the triumvirate of worlds that Penrose tried to think of. He had actually a different diagram in his book. This is from The Road to Reality, A Complete Guide to the Laws of the Universe, which is quite thick. There is another diagram which sort of the arrows going from one world to the other sort of only maps to the whole world itself. In this particular diagram, there are sort of tubes going out, so there might be, he thinks of this is probably is like an inconsistency of doing such a mapping. Okay? But he had a much more ideal mapping, saying that, okay, from all these worlds, you can completely describe the physical world, you can completely describe the mathematical world. Okay? So the mental world that we have over here will be essentially the focus of our talk today, which is the modes of thoughts. Next slide, please. Next. So what as I said, probably in the outline before, there are, I think, well, I'm not mistaken, I think it's four different themes of modes of thoughts that one should have. So the animation is not working, right? Oh, okay. So okay. So the physical world, when you sort of think of it in its true details, it will be often too complex for us to analyze. So what physicists tend to do is to simplify this. And there's a joke about trying to describe a car through a sphere. So this is essentially a metaphor of what physicists tend to do. So what is meant by that is that the physicist would try to remove unnecessary elements or insignificant elements of what they're trying to describe from the theory. Okay, in order when you do that, things will be simpler, and you can actually unravel sort of the underlying physical law. You could probably I'm not the right person to talk about this, but experimentalists often do this in some way. So whenever they try to find a relationship between a pair of variables, so they just focus on those pair of variables, make the other variables sort of fixed, and to try to see the relationship between the two. Okay. Now, for theorists, you have also this idea of simplification by making a toy theory, meaning it doesn't fully describe the physical universe or the physical world, okay, but it sort of captures a few things which the theorists think is essential. Okay, so they build toy theories just to find out what kind of physical law which is operating. So there is a joke. I hope no one is offended by this. They say what theories do is has nothing to do with the physical world, and what experimentalists do is related to the physical world, but they are not quite sure what they are describing because the world is complex. Okay, so let me go to the next slide. There is also some what you call things to you sort of categorize things a little bit when you do all this. You have all these variables to think about. There are classes of variables that one should try to at least understand in some way. You probably have learned this in say, high school mechanics. For example, we talk about kinematics. Okay? When you talk about kinematics, you only involve, say, for example, distance, what else? Distance, velocity, and distance and velocity for that matter. And there will be some acceleration, but it's not actually described through some equation or motion. So these are kinematics. So in a more abstract sense, these are variables that define what we call the state of a system. Okay? And what is essentially a state? It's a complete specification of the system. Given a particular theory, you have to have some variables that tell you about, okay, what's the state of this physical system. You probably know in mechanics it's just position and velocity, for example. Or you can think about the ideal gas. Then you have there are three possibilities there: pressure, volume, and temperature. So you need to pick any two of them. Okay? So it doesn't have to be any particular two, but any two of them. So this will actually completely specifies the physical system. Okay? So these are in terms of kinematical variables. When you talk about dynamical variables, these are things that the variables that actually operate inside the equation of motion. So in the case of mechanics, for example, you have F equals ma, or F equals to dp dt, then you probably need the specification of, say, the initial position and initial velocity or momentum to be able to describe the evolution of that particular state, which is the pair of position and momentum, for example, to find other states after that, okay, at other times. So, and this again depends on what equation of motion there is, and one could actually put more things into that, and it becomes more complicated. Okay, so these are sometimes you might not want to do all the kinematical variables to be in the dynamical variables, as an example. There are also things that we call parameters. And parameters are essentially what I call, or somebody call it, I can't remember who said it, but it's a sleeping variables. So it doesn't really, what is meant by sleeping variables, it does not participate in the dynamics. So normally parameters are actually just given and put into the theory or into the model by hand, and they are normally fixed. If they are not fixed, then probably they do some kind of what you call adiabatic evolution, meaning there will be only small increase, small changes in the parameters. So these are things that one has to be able to do when you try to think of a theory of physics or a model of physics. And I mentioned about models and theories. So what's the difference between the two? Well, models tend to have more parameters. They tend to be, plenty of parameters into the theory. An example would be just the standard model of particle physics. Okay, I'm not quite sure how many other parameters are there, but there are more than 10, if I'm not mistaken. Okay, so there you think of that particular formalism as a model rather than as a theory. A theory tends to minimize the use of parameters, and they are more universal, and they are probably more of a mathematical framework. And these are normally done, for example, in a kind of say, when we talk about theories, we talk about quantum field theory, for example, and within quantum field theory, you can talk about gauge field theory. So this is with respect to particle physics. So they tend to, you have parameters there, but they again are put in by hand, but there are not many of them. Okay? So this there's no real sharp difference between the two, but you have a feeling, okay, when is it a theory and when is it a model? Okay. Next slide, please. There will be a question. Is there somebody? I hope the secretary can, if there are questions, let me know. Given a particular physical system, there might be several different models or several different theories that perhaps can describe that physical system. So the question arises is, how does one actually choose a particular theory or a particular model? So again, this is one of the simplification that people do is to adopt what we call the Occam's razor or principle of parsimony, where, okay, I'm going to use big words now. It's the removal of ontological commitments. When it's if it's dispensable, then you just simply remove this. What's the best example of this? Prior to special relativity, for example, you have the idea of electromagnetic waves propagating in a medium called ether. Okay, but the ether is not necessary in to describe at least special relativity. So it was sort of removed. Okay? You can put it in if you want to. Okay? So let me go to probably a more controversial example, okay? How we use principle of parsimony. You always know, perhaps everyone knows about how problematic quantum mechanics is. there is a problem called measurement problem, where really the measurement problem is because you have what we call the Schrodinger equation, which is supposed to tell you how states evolve. Okay? And then measurement doesn't follow that Schrodinger equation. So what actually happens in the measurement? So there are two different, well, some people call it interpretation. There are two different theories or models, or I'm not sure what to say about those, but here, for example, the collapse theory, it commits to this extra law, so saying that, okay, when you measure the state, quantum state does not follow Schrodinger equation. So you need to be able to describe how measurement actually sort of collapse the wave function or collapse the state in order to give you the measurement results. Okay? So in this way, what's needed is an extra law. This is probably, Penrose view this as something, it's not there in the quantum theory itself. So there is another theory, okay, another interpretation for that. Now, you probably have heard about many worlds. Probably, you're also a fan of Doctor Strange, Multiverse of Madness kind of science fiction or whatever fiction that is. What many worlds commits is the idea that, okay, everything, there will be only a Schrodinger equation. Okay? There's no other equation that needs to be append to the current quantum mechanics. But in order to do that, it has to commit to these extra worlds that seems to be there because you're only seeing one set of measurement outcomes. Okay? So you have these extra worlds, whatever those worlds supposed to be. Okay, one can have different within the many worlds interpretation. There are different ways of understanding the world itself. Okay? So so over there you delete that extra physical law, but you commit to this extra entities of the many worlds. Now, what's your preference? Extra law or extra entities? Given that kind of choice, it's not always easy because extra law means your quantum mechanics is actually incomplete. So, and that's why some of them sort of newer generation of physicists, they tend to accept many worlds, even though it seems to be extravagant because you're thinking of creating a whole world just to describe one experimental outcome. Okay? So I will stay uncommitted at the moment. I will not tell you what I believe in. Okay. So but these are the kind of which one to delete off. So that is the choices that one has to make when there are have different options to consider. Now, of course, that kind of what we call choices is probably the extreme one. But there are other things when you go down to say much more mundane. Well, I mean, down to earth in a sense of describing what's actually the physical processes in, say, in bulk materials. Sometimes you have a different choice of which atomic processes or which molecular processes are more dominant than the other. So these are perhaps less extreme, but you do make a choice. Okay? So do you need to consider even one dominant one and the other ones are less dominant, or you consider all of them as dominant, and then you have a problem how to solve, say, the evolution of the system and things like that. So there are choices. So when you go to the frontier, or that's the thing that you have to face as a physicist. Okay, next one. I'm not sure what's next. Can't remember. Yes, okay. The other thing that a physicist would like to have, essentially, is to consider the physical laws or the physical models that one is thinking should be not specific to a particular situation. No, it should apply to almost every situation. For otherwise, then you have this situation you have one theory, for another situation you have another theory. So it wouldn't be an economical thing to do. Okay? So and physics tend to claim there are some intrinsic nature of matter and energy, and we model certain extraneous conditions, like how you prepare the system or other things. And because of that, you expect some kind of universality. So a medieval example is perhaps the idea of motion of objects in the heavens, the stars, galaxies, and things are subject to the same physical laws as objects on the earth. So this is the kind of universality we tend to assume. Okay? And perhaps so that is probably is a common example that people pick up. Let me go to another modern example. So there's this idea of particles being classified by what we call the Poincaré group. Now, let me just explain this a little bit. It gets a little bit technical. The Poincaré group tells you about the symmetries of the canvas space-time. So you have particles or fields sort of sitting inside this canvas of space-time, and this canvas of space-time have its symmetries. Okay? So what happened over there is that the particles and fields would have to follow the symmetries of the space and time. So there is this theorem by Eugene Wigner, who actually does try to see what is considered invariance of this so-called Poincaré group of space-time symmetries. And probably it's not surprising that probably you think of energy would be one of the invariant, spin would be one of the invariant, and you can have all the classification of the particles that you know, fermions and bosons, which is corresponding to half integer particles and integer particles, are being classified by the local symmetric group of space-time. Okay? So this is a kind of a universal law that appears, but perhaps it's not usually discussed, but no, it's there. So it's difficult to escape from that particular law because it seems to be universal, because it describes the space-time symmetries. Of course, there is some assumption there. Poincaré group is essentially the symmetry group of a flat space-time. So you might have to modify when you go to a different kind of space-time. So, okay, so diagram shows you what are the groups that's being, I can't really see this. So you can look at the I think it's the spin there, and then I think there should be energy somewhere. Yeah. So, but those are actually coming out from the symmetry group of the space-time. Okay. So let's move on. Now, when people claim universality, usually they mean it with a less ambitious claim, okay? Because people know that any particular theory has a domain of validity. Okay? So usually, if you want to have a totally universal theory, you have to stretch all the domains that you know, and this is probably it's very hard to do. To give you an example, is trying to describe the universe, for example. Okay, and you try to describe the universe from the beginning of the universe until the expansion of the universe that you see now, the acceleration of the universe, and you try to use the same physical law. And that's very hard to do. And often in cosmology, what happens there is the fact that you have models for each era. Okay? You don't have one whole set of universal law that describes everything. So you have to partition them into smaller chunks of theory. Okay? A common example probably is much familiar to you would be Newtonian mechanics. It's an excellent theory. Penrose described theories of physics into 3 types: excellent, I think it's superb, useful, and tentative. Okay? So Newtonian mechanics is considered as a superb theory because it can describe a lot of the what we call physics that you see in everyday objects. Okay? But there is a domain of validity of this Newtonian mechanics, which is essentially for those I think the symbols doesn't come out right. Unfortunately, probably because you don't have the fonts for that. Okay, let me just describe what that's supposed to do. What that's supposed to be. That is V very much less than C. Okay? I will share, or maybe I can start sharing so that I can actually do this on my PDF, so that's much better. Let me open up PDF first.
Yes, sure, Prof. You can start sharing.
The only reason that I used the PowerPoint just now was that one small animation that's appearing there. Let me share. So I don't get into, let me go to full screen. Let's see if I can move here. Where will we? Yeah. Just right. So claiming universality for very large domain seems to be demanding, as I said. So the normal examples of this would be the Newtonian mechanics, where the domain is essentially the velocity of the object should be very much less than c, and if you go beyond, you need special relativity. Okay? And then when you talk about classical mechanics, the domain would be this variable S is what we call the action, has to be much bigger than the Planck constant or the rationalized Planck constant. Because beyond that, you probably need quantum mechanics. Okay? So these are the domains of validity that one normally associated with. So you can actually see the picture. Can you see my cursor here?
Yes, Professor.
Yeah, okay. So you can see here in terms of speed here, which is the one for the top domain of validity, sorry. Here, instead of using the action, it uses the size. Actually, if you think about this, this is another good thing to have, especially if you're a theorist or a theoretical physicist. One should think of all these variables or all these quantities that you have as dimensions. And the dimension of the Planck constant is essentially the dimension of the angular momenta, or you can think of it as the dimension of energy times time. Okay? So, or in other words, it also equals to the dimension of linear momentum times distance. So here, when it talks about the distance, it's because you assume that's coming from the momentum times the distance. So you can see that things getting smaller and smaller, one could no longer use the classical mechanics, and one has to use quantum mechanics. And for these two types of describing the domains of validity, you can see that the theory on the right sort of subsumes the theory on the left. Similarly here, and when this happens, you have a sense of skills when it's supposed to be when a particular theory seems to be valid, and when it's supposed to have broken down. Okay? The only thing over here, I think, is very much less for the case of the going from classical mechanics to relativistic mechanics. But it's really problematic going from classical to quantum, or if you want to go the reverse, it's even worse, going from quantum to classical. Part of it is because of the measurement problem that we have mentioned earlier. Okay. So these are things that are there. You want it to be as universal as possible, but there is this assumption of these domains of validity. Okay. So the other aspect that comes with this universality, when you try to think of, like just now, you have a one theory is already subsuming an earlier theory. So in other words, we go to a more general situation. Okay? So when you go to a more general situation, there tends to be new mathematical structures, and the general situation also assumes that the thing that you want to describe becomes a bit more abstract. Okay? An example of this happening would be the idea of inertial frames. Okay? Inertial frames in classical mechanics is essentially those frames that obey Newton's second law. Okay? But as you go to relativistic mechanics, then the idea of inertial frames are very much determined by the space-time structure as well. Okay? So these are when you go to this, going to a much more general situation, you probably need more mathematical structures and more abstract concepts to be involved. An example given here on this second note over here is, I'll go to this diagram in a minute, is the idea of space-time is no longer a simple canvas over which events take place or which particles and fields are residing. But space-time can itself be dynamic. And this happens in general relativity, where in general relativity, you have an equation of motion for space and time as well. And it also depends on the matter or the energy that you have. Okay? And this is much more difficult to think and much more difficult to actually solve. And it uses a very fancy mathematical what you call concept called pseudo-Riemannian manifolds. Never mind if you don't understand those, but in other words, it uses a much more general mathematical concept. Okay. Quantum theory is much worse than relativity because it makes use of I think most of you probably do less of functional analysis, okay? But this is what quantum theory needs. When you go, see, quantum theory are based on what you call operator language. Okay? And this operator language can actually act on infinite dimensional spaces. Your Hilbert spaces, if the properties of physics are being completely described, meaning including position, for example, then it involves infinite dimensional spaces. And these are much harder to think. And that's why going this transition between classical mechanics to quantum mechanics or back are much harder. You are describing things physically using different spaces altogether. Okay, so that's that point. The other thing, the other kind of generalization, normally people don't think of this as such, but it is a kind of, when you go and look at how you classify particles in modern physics, they use what we call group theory. There is a theory of symmetries of how particles supposed to order themselves, just like a periodic table. So you have this notion of symmetry groups coming into the picture as a classification structure. Okay? So it becomes more abstract, okay? And probably you need more what you call exotic groups to actually come into play. The more modern theory, for example, quantum field theory, this is even worse. Okay, you have to consider those which are renormalizable. What do I mean by renormalizable? There, in quantum field theory, you have to do some summation of terms, and these terms are usually infinite. Okay, but even though it is infinite, but if you can what you call redefine them in such a way that it becomes finite, then it's still a kind of a valid theory. And the quantum field theory that which are renormalizable comes into the form of what we call gauge theories. And gauge theories are mathematically described by something else called fiber bundles. Never mind what it is, it's just like another kind of space. Okay, you have your space-time down here. It seems to add more things on top. Okay, and then this extra space that you're considering will have to behave in a certain manner. So if you think quantum field theory is bad, then think about what current physicists or current theorists, for example, the holy grail of trying to unite between relativity and, well, I mean, general relativity with quantum mechanics or quantum field theory. There, we do not know precisely what mathematical structures to have. And over there, you can have this choice. Remember, we we talk about the principle of parsimony. Yeah, so each community, say string theorists will say, look, quantum gravity is bad. Look, quantum gravity says, okay, string is bad. I have a personal experience, but it's not because of the physical content of those theories. It's just the attitude. But I will not say anything more beyond that. Yeah. So you find that certain communities tend to behave a little bit more unruly in some sense. Okay. Right. So let me go to the next one. Okay. So here is another aspect that usually normally physicists would not want to say too much. But let me first talk about, remember the idea of making physics related to maths. And there are assumptions being made there about what kind of number system that one should use. Okay, you can talk about natural numbers, integers. So integers includes negative numbers. So is negative numbers physical? Rational numbers, are they described physically? Real numbers, are they really there? Okay. If you think of how mathematicians construct those, they are rather artificial. But the Greeks have a way of thinking about it. The Greeks tend to think of it in terms of geometry. The geometry are more or less described by sort of distances and things like that. And now, after, well, essentially is even before that, but quantum mechanics seems to say that you need complex numbers. It's usually it's an unfortunate name that complex numbers has this, you know what they call the real part and the imaginary part. And this is an unfortunate labeling of those numbers. So you think that the real part is more real than the imaginary part, right? So, but that's not it. Okay? It's just saying that, okay, you have this imaginary part, which if you learn about maths, there's always a way to extend your numbers. Okay. For example, you can, one of the things that you probably have not learned too much would be the idea of what we call quadratic extension, where your numbers, sometimes if you have it in terms of a square root 2, for example, then you find that, okay, whatever algebraic equation that you have that has this algebraic, it's called algebraic numbers, the square root 2 there, then it will come in pairs just like complex numbers. Let's say 1 plus root 2 being a solution to some polynomial equation, then you should have also 1 minus root 2 to be a solution of that polynomial equation. So you know that the so-called imaginary numbers, when you solve, say, a quadratic equation, ax squared plus bx plus c, for example, then you need your b squared minus 4ac to be greater than 0, so that when you take the square root, you get real solutions, right? But if b squared minus 4ac is negative, what you get is a different type of solutions called the complex solutions. And believe it or not, this is normally not taught. If you think of how the quadratic equation describes a parabola, okay? So you can think of, the doubly degenerate root will actually touch one axis at one particular point. Then you have this degenerate roots. Okay? If it cuts across a particular axis, then you have this sort of pairs, okay, pairs of roots. Now you imagine now if it doesn't intersect, if it doesn't intersect, the parabola doesn't intersect with your axis. Now geometrically it's there, right? Of course you cannot see how you can actually solve the equation, but it's supposed to be there. And that is precisely where that geometry, okay, with the parabola is not cutting across, say, the x-axis, for example, describes essentially a complex solution. Okay, so these are things probably one assumes there I'm using the idea of geometry of lines and curves to actually describe. So there are things probably one assumes in that particular way of what number system to actually to adopt. Okay? But besides even this number system, remember why do we have this number systems? To make your analysis to be quantitative. Okay? Without number systems, then you can talk about words, which you can't quantify. So you need to put them into numbers. Okay? But that theories also contain something even beyond that. Usually you put into the theories something which is not really directly measurable. Now, perhaps the way I'm describing will not probably a common way of people looking at it in a philosophical sense. But take an example, this debate between the two schools of thought prior to quantum theory exists. Okay? Boltzmann has been struggling to put his idea of atomic theory to describe statistical mechanics against this another camp, which is from the thermodynamics sense, which is essentially what the common term that people use is essentially energeticist. It's a bit difficult to pronounce, but the energeticist say, okay, with describing in terms of energy, you are actually empirically grounded. You are just using physical concepts that you can actually measure. And Boltzmann, who used this idea of atoms, is considered fictional. And in the end, what happens is that this fictional theory tends to give more explanation. And even Planck, when he started off trying to describe black body radiation, for example, he was hesitating to use Boltzmann atomic model. Initially he was from the energeticist kind of camp, trying to describe in terms of energy rather than just using idea of atoms. Okay? But he later he has to adopt Boltzmann atomic model in order to explain the black body radiation. Now, but second thing here, okay, the second last thing that I want to bring in the idea of you putting things in which is not really measured. Quantum theory posits in a way. Okay, how one describes a quantum theory as a geometry? It uses what we call a projective geometry, and projective geometry we use some kind of symmetries which involves projection. Okay, so that's why it's called projective symmetry. And this projection involves some hidden degrees of freedom, or the fifth degrees of freedom. And that's why, for example, instead of talking about angular momentum as just simply the orthogonal group of rotations, you allow to have the idea of unitary groups, SU2, which talks about the spins and things like that. And spins spin is not really angular momentum that arises from motion. Okay? So these are things that comes into picture that normally people do not want to describe this as something which is unmeasurable, but it's really unmeasurable. Of course, these phase degrees of freedom, you could measure it if you allow the system to be interacting with other things. Probably I do not want to go too much into the details. So there are things normally put into the theory which is beyond what we consider as directly measurable. I want to give you another example because this comes close to my sort of experience in some way, because I was taught by a person who gives an alternate description beyond quarks and colors, degrees of freedom. Prior to introducing color charges, okay, there is this generalization of the spin statistic problem. Remember earlier I mentioned about the Poincaré group giving you just your half integer spins or integer spins that gives you the fermions and bosons. Okay? But there is a generalization of this group that gives you what we call parastatistics, that gives you sort of a statistic between fermions and bosons. I mean, it's a bit difficult to actually describe it. But this parastatistics was earlier considered to help solve the bound state of what we call the hadron omega minus. Omega minus is essentially a bound state of the strange quarks. All of the quarks are strange. So there is a problem of what kind of statistics that they are actually behaving. Okay? If there are 3 quarks, then it's an odd multiples of spin half. Okay? But yet, it doesn't quite fit that picture. So parastatistic was actually introduced by Herbert Green. Herbert Green was my lecturer in University of Adelaide. Okay? He introduced how to quantize fields in general way back in 1953. And of course, that was even before they considered the quark model we believe in, okay? So when they found that omega minus hadron to be a problematic case, then they were thinking about using the parastatistics. But later on, it was actually shown that, okay, the hadrons actually behave differently because there is another degree of freedom which is associated to the strong interaction called the color charges. So the color charges was introduced later, and then Herbert Green and Bracken, for example, actually shows there's a correspondence between taking parastatistics only without the color charges and talking about the normal statistics, but now with the color charges. You can make the correspondence between the two. Okay, so there again, you have the choice. You remember the principle of parsimony? Okay? So which one do you want? Well, it seems that in terms of the larger committee that adopts theory, it seems those are the ones. The larger ones are the ones that adopt the color charges. Even though at the time it was not really observed, sometimes people do actually adopt that. So this was why I'm telling this story instead of some other more famous story. is because Herbert Green was my lecturer. And the way he thinks is totally bizarre. Sometimes one of the experience I had, I think if somebody had actually gone to my earlier lecture in USM, I thought about he's probably the most original lecturer that I had, because if you try to find what he writes in his lecture notes and what's in the books, there never seems to be any correspondence. So you have to think about say you have an assignment problem. You have to think in yourself how to do it. So that was to me it's one of the most valuable experience that I've gone through. Okay, it seems like the previous example. Okay, don't believe in atoms or believe in atoms. Atomic model wins. Don't believe in color charges or believe in color charges. Color charges win. So you might say that, okay, all these things seems to say that, okay, try to adopt something which is not really what you call there measurable. Okay, but don't be fooled by successes. There are cases like prions and rations, which are sort of more fundamental particles beyond quarks and leptons. Okay? But this has become unfashionable. It may be reconsidered in the future, but so that sort of falls out. Yeah. Okay? Now we have speculations that people think about. Okay, how to unify all these particles together. Okay, why do you have only fermions and bosons? Why not have a symmetry that converts fermions into boson and bosons into fermions? And this is precisely the idea of supersymmetry. Okay, and then if you localize the supersymmetry, then you get supergravity. These are all ideas proposed in early 70s. But what happens in this is, in this type of theories, it doubles the kind of particles one expect to have to appear in particle physics. But so far, this has not been seen yet in our current accelerators. And that's why people campaign, okay, we do not bigger accelerator in order to find all these extra particles that one needs to have in supersymmetry and supergravity. The other speculations that people do as you go to the frontiers, okay, as you go to the frontiers, you go into more abstract mathematics, as I say, and you go into more philosophical considerations. So loop quantum gravity is an idea of trying to quantize gravity without using even all these new ideas of supersymmetry and supergravity. So meaning you can actually quantize generativity, provided you adopt the right variables. Okay? So again, the idea of choosing the variables seems important. So once you adopt the right variables, then you should be able to find that space-time are also discretized into discrete areas and discrete volumes. Now, the other popular community is those coming from superstrings and brane theory. So the conceptual idea over there is not to consider point particles as the most fundamental objects, but to consider something which is more extended. And there are many claims within this community, and they have, if you want to think about the new type of maths being generated and as an indicator that is the truth, okay, then superstring and branes would be probably, because they generate a lot of new maths, okay, unlike loop quantum gravity. But loop quantum gravity, in one sense, is a bit economical in terms of ideas. Superstrings and branes, you start to introduce supersymmetry as an extra law. You start to introduce extra dimensions, which apply principle of parsimony. Which one do you choose? Okay. So now, okay, there is another school of thought. Perhaps we are doing the wrong geometry. Okay. So these are ideas proposed by Alan Kohns, a field medalist. He's a mathematician more than a physicist, but he tried to build up a new mathematical theory where your geometry is actually governed by operators, which is essentially the language used for quantum theory. And spelling mistake, non-commutative. So this new geometry becomes the new canvas for quantum particles and fields. So these are again speculative. There are successes of how they model unified theories, but again, people have their own point of views. So they argue within each other. So the other one would be, again, I'm mentioning this because he has certain personal experience. Sometimes probably what one needs is perhaps remember the number systems that we assume. Okay? Perhaps this should be reconsidered. Maybe the Boolean logic, for example, is essentially is like 0 and 1 or 1 minus 1 kind of number system. Okay? You have yes and no. But it's possible to consider other types of number system. And this is an idea given by Chris Isham, where it starts to use a different type of logic into the theory of quantum physics. Okay? So there, in the hope that it explains better quantum theory, unlike the present quantum theory that seems to suggest a lot of bizarre and strange things. So again, the research program started there. I mean, it has not been completed. Okay? People start to use his ideas, but no, it has not developed to the point of actually reproducing quantum mechanics as a whole. Okay. Okay. How much time do I have left? How much time do I need to?
Perhaps until 11:45.
Okay,
Yeah.
to finish up.
Okay.
Okay. Now there is another. Not sure whether you can actually see this. There is another lane of thought. Is to consider, okay, maybe we are pushing too hard on the physics frontier. We should consider going beyond and try to describe the other branches of sciences. Okay, mathematics has been very close to physics, so not much surprise there. So the other sort of basic sciences is chemistry. Chemistry again is very close to physics. You can see that they share the same description from quantum theory, for example. They use the same tools like density functional to describe both physics and chemistry. So, I'm going to leave that one out as well. So, what are the basic sciences? Biology. Okay? So, biology uses a lot of tools that comes from physics. Okay? So there is this, if you look into the archive, for example, there is a sub-area called quantitative biology. And this quantitative biology uses mathematical tools which is shared among different areas of physics. But recently, there are now people trying to put forward the idea of quantum biology, where you have quantum interactions and biological processes. I think it's still very young. And some successes are essentially your photosynthesis and DNA mutations, which I know very little about. So please don't ask me on that. Now, coming back to remember the two additions in the physics subject heading? So if you want to go beyond, probably those are the promising ones. Okay. So there is two new additions, which is networks and then quantum information. Okay. So what essentially is networks? Networks are essentially, it adopts a traditional mathematical tools called graph theory. So graph theory is essentially how you make connections between nodes using edges and things like that. So here's a graph, a very complicated graph. I believe I've shown this in my previous talk. This is a graph depicting the relationship between one classification of subject inside the archive with another subject. So one could actually see, might not be so obvious, but there are information sort of emerging out from those kind of networks. So this has become tools, for example. Now networks has been used very much earlier on in social science. They talk about community of friends, for example. Before Facebook was actually sort of control the data being made available to the public, I used to actually map my friend networks using Wolfram Alpha. But now, since that data is now being limited due to cases like essentially you're taking a private data. So I cannot do that anymore. So I used to have, I can even see, okay, my school, my Facebook friends are sort of lumped into what I call communities. And I can see, okay, this is nature. These are my school, high school friends. But there will be some connections that seems to be very interesting. So these structural properties of these graphs actually convey information, and people have been using that to analyze things. So that is one. In fact, one of the things that I wanted to start off in the Institute of Mathematical Research was this idea, because I have not seen this being used apart from probably Professor Guru group in Wisdom Layer. Okay. So I wanted to start it off in UPM. With not much success, of course. Right, okay. What's the other one is the idea of quantum information. Now, quantum information science, actually, they say there are two revolutions in quantum theory. First revolution gives you the essentially the semiconductor industry or the electronics. Okay? But there is now a new second quantum revolution that's supposed to give you direct access to quantum phenomena. And these are now being developed into what they call quantum technologies. Okay? So this is very much related to the idea of quantum information science, being the amalgamation of quantum physics, information science, and engineering. And it really has its roots from the quantum foundations, things that like the measurement problem, for example, just now. Okay? Arising from a measurement problem is the idea of entanglement, how far away particles could actually have correlation between each other. And how do you understand that? Okay? So this has been used in quantum information science, and over there, I'm still trying to get used to the different thinking style. The different thinking style here is more engineering-like. So engineering-like is like, you're trying to build products all the time. This is not the way physicists think usually. Physicists think is always to describe how the natural world is actually behaving. But here is a more engineering thing where you have a purpose. And then you try to, okay, can we use the quantum properties to come to that particular purpose? So it requires a different kind of style of thinking, which as a physicist, I'm still not used to this, but no, we are trying. Okay, so so these are things like building up quantum circuits in order to. This is just like a program, really. You want to calculate certain things, so you have a purpose right from the beginning, and then you do some logical operations in between in order to arrive to that particular purpose. So you have to have that thinking style in order to go into the quantum information science. So that's the beyond physics. So perhaps I will rush through my personal journeys. Despite what you know about me, I do not know anything about theoretical physics until my third year of Bachelor of Science, which is 1983. I was just an average student most of the time. And then when I go into the third year, things becomes much more specialized, and then I found out about mathematical physics. They have a department of mathematical physics in Adelaide, and I did my final year project there. And this is essentially the final year project topic, which is on minimal SU5. SU5 is the symmetry group that people adopt to unify strong, weak, and electromagnetic forces. Okay? And there is this model which we call minimal SU5, but minimal SU5 seems to be inadequate because there are some problems like fermion masses, proton decay, that cannot be explained by just the minimal SU5. Minimal SU5 eventually get your single Higgs. But you have other Higgs, but you probably it gets too heavy. So you need to modify those. So you consider more Higgs, and to a certain extent, I say this just like a game. You put more parameters in, and then of course you can, with more parameters, you can simply fit any kind of physical environment or things that you want to have. So with that final year project, I graduated with first class honors, and let me just, I'm not trying to boast here. I have a reason why I put that in. Because I thought I was clever enough already. By the end of this, my what you call undergraduate studies, I was already reading literature on supersymmetry and supergravity, and I thought, okay, I should be doing this kind of thing. It's exciting, you try to unify fermions and bosons, and then you also get gravity as well. But with supergravity, you need also what we call gravitinous, which is not seen, of course. And my undergraduate studies come to an end. I was on a Ministry of Education scholarship. So I was supposed to be trained as a teacher. So I had a brief stint at Mata Perguruan Temanggung Ibrahim in JB. But I thought that I wanted to do more because I wanted to do research. So I applied for tutor in UPM in 1985. And then once I joined UPM, I started to think about going for postgraduate studies, and I applied for part 3 of mathematical tripods in the MTP. And part 3 at that time was given as advanced postgraduate diploma. Nowadays, part 3 is considered as a master's program. Okay? So you can look it up. That is actually equivalent to a master's course. Okay? So I joined University of Cambridge join the colleges there. They have a different type of system from the ones we have here. It's not just residential college. It's supposed to be have an academic college as well, where you have personal tutors. Unfortunately, because I think I was already a postgraduate, so I joined Darwin College because it was labeled as a postgraduate college. And there were not many people there who are actually doing part 3. And there are not many personal tutors that I can actually consult. So I was in the wrong community in some sense. And my part 3 class in the AMTP is where Stephen Hawking is. Okay? There were about 40, 50, 40, I don't know the exact number. It's about 40 to 50 students from all over the world. And you can imagine the kind of competition there is. So I completed that course with a part 3 essay with an index. You can actually see in this particular picture here. I didn't do quite well, unfortunately, meaning to do a PhD, to continue with the AMTP, for example, I will have to be in the top 10 among these 40 to 50 students. Of course, I was not, okay? Too many brilliant students. And this is a sort of experience that I find, okay, I thought I was good enough, but still not good enough, okay? So you see all these brilliant students. I saw one student, Nigel Burrows, keep bringing his study bag into the lecture theater. It's now, I think, in Warwick. So here I have all these bright students. The best student was actually Faye Dowker. And she's a daughter of another theoretical physicist. So I thought to myself, I was not really prepared to go to Cambridge. Despite doing well in my undergraduate, I think I was not really prepared. So, but I passed anyway. I have students or colleagues actually fail this course, meaning they didn't get their certificates. So it was not an easy thing. It was one of the most difficult time, and sort of my morale sort of went down a little bit. But I met my potential supervisor there in Cambridge, went to a particular conference in Cambridge at the time, and met him and said, okay, come over to Durham. And I went there with a few of my friends who was also doing this part 3 mathematical triangles. So I applied for PhD in University of Durham at the end of 1986. Richard Watt, who I already mentioned, met in Cambridge, and he was a disciple of Roger Penrose. So I have an academic grandfather who is a Nobel laureate, but no, they do have this sort of tree, looking who's the student of what, a student of what, So I was the grandchildren of Roger Penrose, because my supervisor was a student of Roger Penrose. So I did a PhD thesis on group theoretic quantization and central extension. Essentially, this is based on a work by Chris Isham. That's why I mentioned Chris Isham earlier. And he was my external examiner. This is Chris Isham over here. But this is not during my Viva. This is actually, I can't remember what year was that. I was visiting him under the Royal Society and Academy of Science Malaysia program. So one of the things that I've learned through from my PhD experience and from my part 3 experience is that despite that you think you are good enough locally, always know that there will be much better people, much talented people we consider the whole world. So when I went back, okay, I think I'm not that bright, but I think I'm capable, but I wanted to do something new. Okay? And I was doing quantization, as I said. And then I read this book by Ashteka. Ashteka is a quantum related to loop quantum gravity. And he wrote this as a preface to his book. Remember I mentioned about quantization? There is now a clear quantization program based on algebraic ideas. The need for sophisticated techniques from geometrical quantum mechanics no longer exists. When I read that, my heart sank very low because that is precisely what I did. But for my PhD, there is a novel element because what I did was to look at system in external fields. So the external fields become my parameters, that theory. So how to deal with those? So when I came back, was still thinking of what to do. So immediately after I reached my office, I was assigned to go to UPM Bintulu campus. And over there, they are just teaching diploma, so I didn't do much over there. So when I came back to UPM Serdang, so I tried to extend my PhD work. So I attended the first international conference. I'm not sure before that whether I attended any conference at all. I think this was the first. There was a 5th Asia Pacific Physics Conference. I presented a paper there just to extend a simple extension in my PhD work was dealing with a torus. The torus looks like a donut, so you generalize the number of dimensions to dimension n. So presented it there. Some international physicists come to approach me and say, the person I can remember very well, Professor Lei Nam Chang, from Virginia, in USA. I think I think there's some nation origin connection there, but he came to say, hey, your work is actually related to quantum Hall effect. So I said, okay. I didn't know too much about that. So, and then when I joined the physics department, the physics department, as I said earlier on, most of our physicists, local physicists are condensed matter physicists, really sort of experimentalists. So I was advised to work on something which is probably beneficial to the department. So, okay, then I tried to choose quantum Hall effect. Again, this is also related to the fact that it's a system with external fields. Okay? And to do this, the main problem in quantum Hall effect is to understand fractional quantum Hall effect at the time. So in order to have this, and fractional quantum Hall effect is coming from a many-body effect. Okay? So I had to sort of modify the kind of space that one wants to work in. And this is essentially, I call it punctured surfaces, meaning you remove certain points, or actually the points that was removed is actually goes to infinity. So what we have at that system, this is again a toy model. Remember the toy model I mentioned earlier? Okay. This is actually a hyperbolic surface. So we work on that. We try to do it sort of analytically, and I had a first PhD student, is Ahmed Bukater. Now he's in Saudi Arabia for, I think, theoretical physics center over there. I can't remember precisely, but the description is there. So, and his external examiner was again the same external examiner that I have, Chris Isham. And at the time, nobody cares about our work. So, and then when we did this, I stumbled into a problem that one can differentiate too much between one punctured surface to another punctured surface. So remember, you can introduce punctures in various different ways. And oops. Okay, maybe I should continue that later on. So that was the beginning of something that I tried to do locally. Okay. So to pursue my dreams, what I did was, I spent a lot of money. I subscribed to, this is not International Journal of Modern Physics A and Modern Physics Letter A, right from the very first issue, and this is published by World Scientific. So, I had for several years, I think. And then, most of this, the content over here is high energy physics, and which includes experiments and phenomenology, which I was not really interested in. So I started to subscribe a different journal, which is Review in Mathematical Physics. And the first issue was in 1989. Again, I subscribed for a few years, and then I stopped because I couldn't no longer afford it. And I wanted to go into geometry and physics. So I subscribed to this. This is actually from a different publisher. But again, no, you think you want to be a specialist in those areas, but in the end, you stop because you just don't have enough money. Then I subscribed to science because I started to do administrative work, and to be an administrator in charge of a research institute, one has to have a very broad view. So I subscribed to science. Okay. And again, I stopped after a few years. And I spent a fortune on hundreds of books, which I still keep. Actually, for the journals, I've already donate this to mostly to my theoretical physics group in UPL. So what are the research programs that I've started to do? These are the research programs. So initially I did that, but I find that the algebraic approach that one does it's not sensitive enough to look at different punctured surface. So then I continue with a more numerical approach. So down here, but of course I also do other things, Cohen-Specker theorem, Bianchi cosmologies. I tried to do complex network, then because it involves too much, you have to do a lot of manual work in some sense, which I do not. I love mathematical formalism rather than doing all this manual work. And then this currently the two programs I'm trying to finish off, the geometry of quantum states and entanglement, and then symplectic topology with quantum states. Other things that I've done essentially to start off a lecture series. I don't want to claim to boast, but in those times there were not many lecture series. I don't think there was any in UPM at that time. When we started off the lecture series, we sort of starts a trend, and then I was went from one institute to another institute, and I renamed it to Expository Quantum Lecture Series Equals. Yeah, so that was Equals has still going on, but now organized by my junior colleagues. And then while I was the deputy director in the Institute for Mathematical Research, we had some Italian visitors, and we tried to do some paperwork and then establish Malaysia Italy Center of Excellence for Mathematical Sciences. This is essentially agreed from one ministry with another ministry. Okay, so it is, but it's an informal kind of body. The office is placed under INSPAM. So hopefully this, again, when you're a physicist, you should be thinking about what should happen when you leave, what should happen to the younger theoretical physicists or the younger generations. So I believe in something what we call, sometimes what administrators do is they try to constrain things. I prefer to have this idea of trying to expand things by creating opportunities. Yeah, so by doing equals and doing my sense, I hope you actually have more opportunities in the future. So here some pictures of the equals. So this is the first equals that we did. So here's Kyo Liping from Xiamen, and T. Bon An from Nottingham University, Malaysia. So we tried to work together. T. Bon An was my first postdoc. He returned from Texas and then contacted me. So at that time, postdoc was a new thing. So he went to UPM. So he was my first postdoc. So we did try to do events like equals. So these are the first equals that we did. And then we do subsequent one. And then we do conferences. This is something that we did. Was the Asia Pacific workshop and conference and workshop in quantum information science. So we bring it to Malaysia because I was in the circle of the standing committee. So we did those, and of course I mentioned about my SAMs. So here, myself, this is a Deputy Vice Chancellor in the past, former Deputy Vice Chancellor. Here is Lamberto Rondoni, the Italian mathematical physicist, and we sort of clicked together and trying to discuss ideas. Here was the Italian ambassador at the time. And here we have our Deputy Minister of Higher Education during the launching of the National Italy Center of Mathematical Sciences. So that was the things that I do. So probably I should stop. Thank you. So I should stop sharing, right?
Thank you, Professor Dr. Shamadin, for your enlightening speech. Before we continue with our next session, let's have a 5-minute break, and the link for the Padlet will be sent at the comment section. You can post your question. There, and we shall discuss the discussion on the Q&A session later. See ya in 5 minutes. time flies. Our 5-minute break has gone and we are back to discuss more interesting yet knowledgeable topic. Alright, ladies and gentlemen, now we come to Q&A session. This session will only last for 20 minutes. I repeat, the Q&A session will be open only for 20 minutes. If anyone have any question, I'm sure our guests will be pleased to answer them. You can turn on your mic to ask our presenter this question or leave the question in the Padlet link provided. So I will start with the Padlet questions. Good morning, Doctor. Our current university physics syllabus is somewhat still lacking of theoretical physics subject. Any further mathematical topics would you suggest our interested student to self-studies?
Yeah, I'm not sure what the question is there, but yes, it's true. Our curriculum is probably much more inclined towards the applied physics stuff or condensed matter stuff, and which is fine. But again, as I said, I'm a person who wants to create opportunities rather than constraining people. Yeah, so these are probably the best way to think. But we also have another problem is the fact that our numbers are still small in terms of the theoretical physics in the country. So this has to be done gradually, I suppose. Again, with respect to courses, I think we have started certain courses. In UPM, eventually we're going to have a quantum information course offered by the physics department. So again, these are done gradually rather than one can just do this overnight. I wish one of the dreams when I joined UPM, I wanted to have all the things I have learned, try to put them in place. But of course, being few of us, there's not much we can actually do. And also, the other thing is students tend to run away from difficult subjects. So I'm not sure what to do about that.
Okay, thank you, Doctor. We continue to the next question. What advice would you give to the young blood thinking of going into theoretical field? The
Well,
question is the one yang bercolour.
who was the person? Okay, now I'll try to answer this. Again, as far as it has to be internally motivated. That's not because if you depend too much on external motivations, then there will be at some point you face problems and there are no support group. There's no support group that actually can try to help you. So we in UPM, for example, we do have a group. We do have a group with my junior colleagues and the number of students that we have. We form weekly meetings, okay, and try to participate in those types of groups. And what we did was usually, we tend to have weekly meetings, and everyone can present whatever things that they have read. And one of the things that I wanted to have is that discussion thing, okay? The Q&A, because we are lacking that kind of discussion within our local environment.
Thank you, Doctor. I'm very agree with your opinion. As for me, I do love physics from my secondary school, but this sem I feel like it was so hard because now I'm facing the quantum mechanic subject. I feel like taking physics is a mistake somehow because we are too busy catching the syllabus, tests, and exam until we forget that it is our passion. I don't know, somehow we lost track in order to get good grades. I don't know, just my opinions. So we shall continue to our next question. This one is interesting. What do you see for quantum theories in Malaysia in the coming 10 years from now? Do you think we will be part of frontier in the world's quantum research?
You want my pessimist side or the optimist side? Okay, put it this way. We do what we can. I think this is the reason I've been telling my junior colleagues and even students that one thing lacking is we want to build a tradition. Okay? Because what happens in the past is that when one theorist retire, the tradition sort of stops. And then if somebody wants to continue in that same area, has to start. The person has to start from scratch. That should be, if best, avoided because you want to have that continuity. Because if you keep stopping and then build from scratch again, stop, you will not progress much. It will be very slow progress. So if you want to have a tradition, you have to have continuous sort of younger people doing the whole subject. So thinking 10 years ahead is probably too far. But we tend to discuss these kind of questions, but I do feel that we have progress. We have progress. The only thing that we want to make sure is that it's sustainable.
Thank you, Doctor, for the very complete and compact answer. So we move on to the next question. I believe that everyone here would love to study abroad. Right, so one of our participants asked that, do you have any further study abroad suggestion? As in which institution we can apply for enthusiastic undergraduate physics student in Malaysia?
For undergrad or for postgrad?
Instead for undergraduate. The participant asked for undergraduate.
Again, if it's a general undergraduate thing, probably you just want to, you have to think slightly beyond undergraduate, because if you feel that you want to be trained in certain areas, you look for universities which are excellent in those areas. Okay? Because when you have excellent people there within that particular area, then you most probably, more often than not, you will get training which is valuable. So you have to think slightly beyond your undergraduate. Because undergraduate is just a starting point, really, for whatever area that you choose to pursue. I'm not sure whether that answers.
Okay, thank you, Doctor. I think I will take one last question. Is if that okay?
Okay, sure.
Okay, for the one last question, I'm gonna read this one question for your effort typing long question. People have been saying that particle physics was a traveling research field before the 20s, but now they view it as a scam or fraud in physics because according to them, they purportedly say that it leads us to nowhere, which I personally don't believe it. But plus, recently the W Boson news had give us some hope that it might not lead us to nowhere after all. So, what is your opinion on this statement?
Oh. Certainly, I think it's a scam in the way it's been described. But certainly, no, administrators, put it this way, administrators, whatever organization is supposed to be, they have finite resources. So these are the difficult things that people have to decide. So whatever it is, to continue a particular pursuit of an area, it really needs a lot of deeper thinking. So meaning that the resources are, how should I say, when it's being allocated, it's being used as effective as possible. So of course, one has to be very careful about the kind of, I can't find a word for that. It's not scam, but things like you exaggerate things, or you exaggerate the benefits. I think that's of course you want to publicize things, but in the end, in the long run, it will hurt the person who wants to promote whatever area there is. So be very modest in some sense of what you want to achieve, and then make sure you don't exaggerate what you're trying to do. I think that will actually eventually help you, even though the publicity will be less. I'm not sure what the question we're getting. Well, the particle physics thing, of course, I think is a worthwhile pursuit, but it really requires the collaboration with international groups. I don't think we can do it ourselves, at least from my point of view. So I think what our National Center for Particle Physics is doing, having some collaboration, I think that's worth pursuing.
Thank you, Doctor. Ladies and gentlemen, we finally come near to end of this program. But for now, let's have a photography sessions together. So please turn on your mic, turn on your camera together. I give you all about 1 minute to open your camera. Okay. Anyone else want to open their camera? I give 30 seconds more. Okay, are you guys ready? Media team, are you ready? Can put thumbs up. Okay, ready? 1, 2, 3. One more. 1, 2, 3. Okay, last one. 1, 2, 3. Okay, thank you. Excuse me, doctor, can you please write in your email for the unanswered question just now, so they can just email you or keep in touch with you.
Where do you want me to write this? I'm not sure. In the chat?
Yeah, maybe you can just give the person in charge, and then we can sort it.
I'll just give my personal email because I'm retired. Okay, so
Okay.
sorry.
I would like to say great thanks again to Professor Dr. Hishamuddin for your time, effort, and also valuable information you give. Wish you continued success. I hope everyone can put the knowledge and tips in our daily life. Thank you very much, everyone, for your active participation in this program. Once again, let's give our speaker a digital round of applause. Before we end our talk today, I'm excited to tell you guys that second phase of registration as audience in NPUPC National PZ Undergraduate Project Conference is now officially open again for you guys to grab this final last chance. It will only open from 29 May, which is today, until 1 June of 2022. So what are you guys waiting for? Sign up now, join us for more interesting knowledge, and be part of our big physics conference. I think that is all for me. Thank you and have a nice day. Bye-bye.
you.